Okay, so let's keep going with the weirdness and insanity that are photons. So the next thing we're going to go over is called the Compton Effect. And so this guy named Compton determined that photons have momentum, which is actually pretty crazy because if you remember back to momentum, that's equal to mass times velocity. Photons are light and therefore they don't have mass, so I don't know how they're supposed to have momentum, but they do. So how did he figure this out? He did this experiment where he beamed X-rays with a known frequency at a thin metal foil. And now, yesterday we figured out when we shine visible light at certain metals, then electrons will be ejected. So of course this is happening as well, but so he just did this with even higher frequency light with X-rays. So notice the electrons are emitted just like with a photoelectric effect. But with the photoelectric effect, those photons were completely absorbed. These ones passed through, and some of them had the same frequency as the incident photons. That means they probably collided with nucleus or empty space, but some had a lower frequency, meaning a longer wavelength. So some of those X-rays went in, they collided, of course gave some of their energy to the electrons, but then they kept going through because X-rays have a significant amount more energy than visible light, and they had a lower frequency or a higher wavelength. So it actually changed the makeup of the X-ray, which is pretty cool. So of course, classical physics can't explain this because they were like, well, the rays would just be scattered, but you can't just change their frequency, right? That's not something that happens. So we needed our modern quantum physics to help us explain this. And the explanation is that photons must have momentum because really this is kind of their version of running into something and changing their velocity, but in this case they're changing their frequency because we know photons can't change their velocity. They're always going the speed of light. Okay? And that in that way then we can have this conservation of momentum between electrons and the photons of the X-rays. Okay? So it's similar, Compton is similar to the photoelectric effect where of course we have EMR strikes a metal plate, electrons are ejected. But the photoelectric effect, again, uses the lower energy photons, i.e. visible light, and they don't exist after they've been collided because all their energy is taken up to eject the electrons. But Compton, since they're much higher energy photons, they scatter. Okay, some of them go right through and then some of them kind of scatter the other way, but they have a lower energy and a lower wavelength to them. We know that momentum is usually equal to mass times velocity, but photons don't have mass, they're light. So yes, light is a wave that acts like a particle sometimes, but that doesn't mean it actually has particle-like properties like a mass. It definitely does not. Light has no mass or else we would be crushed underneath the mass of all the light right now. So we have to use something called a mass energy equivalence, and this is this super famous equation that you probably heard of but you had no idea. And the fact is that things that have really, really, really high energy can act like they have mass. So that's how we get the mass energy equivalence here, and that is E equals mc squared. So they're acting as if they have mass, but really what they have is just a ton of energy. So we can figure out how much energy they have and how that much mass that would be equivalent to using this equation. So if we rearrange this for mass and what the equivalence is for a certain energy, that's energy divided by c squared. So let's plug that into our momentum formula because we know we don't actually have mass. So instead of momentum equaling mass times velocity, the mass is going to be E over c squared, so the energy of the photon divided by the speed of light squared times its velocity, okay? And we know, of course, the velocity is the speed of light. It's also c. So we have E over c squared times c, and then one of those c squareds cancels out with that c. And so you get momentum of a photon being E, the energy of it, divided by the speed of light. Now, sometimes we don't always have the energy of a photon. We have to find it. So remember, one of the equations for energy of a photon was h, Planck's constant, times its frequency. So let's substitute that in. So then we have the momentum equaling hf divided by c, the speed of light. And then again, that can also, if you have the wavelength instead of the frequency, then we can also put wavelength in there instead, because of course we know that c, speed of light, is equal to frequency times the wavelength. And therefore, I know it's weird that I'm putting it this way, but 1 divided by the wavelength is equal to f over c. Why am I doing that? Because we have f over c there. So therefore, that's the same as 1 over the wavelength. So another equation that we can do there is momentum is equal to h divided by lambda. And that is the equation that you have on your data sheet for the equation of momentum of a photon. Okay, but that is how you derive that formula, and yes, you could be expected to be able to have to do that. So definitely take note of this equation. We're not seeing the end of it today. We're definitely going to use this because if momentum is equal to h divided by the wavelength, then the wavelength of something is equal to h divided by momentum. And if you think about that, momentum, we then again have another equation for that, could be mv. So could we possibly find the wavelength of a particle? I don't know. We're going to have to wait until we get there. So remember, you can't use equations with c to solve for a particle with mass. Okay, c is only for EMR. It's only for light. And you can't use just kinetic energy equals 1/2 mv squared or momentum equals mv for photons. They have no mass. Okay, so when I ask for the momentum of a photon, you better only be using this equation or one of the ones that I gave you that is equivalent to that. Okay, a lot of times when I ask for energy of a photon, people try to use kinetic energy. When I ask for momentum, they try to use P equals mv. You can't. Photons do not have mass. They act like a particle, doesn't mean that they are. So let's go over this Compton scattering a little bit more and what kind of math we can do with that, because now we're back to conservation of momentum and that happening. So when an X-ray scatters, you have the collision of the photons with the atom, and that demonstrates conservation of momentum. So therefore, we can kind of treat this as an elastic collision where all kinetic energy of the system is conserved, momentum is conserved, and this is truly an elastic collision. If you remember from the momentum unit, no real world collision is elastic. That is where all kinetic energy is conserved. Every single collision that we went over that wasn't at the atomic level was definitely not an elastic collision, but collisions at this level are definitely elastic. So we are finally there. But of course, remember, if it's an inelastic collision, only momentum's conserved. So the nice thing about the fact that this is an elastic collision is that we can use conservation of energy in place of conservation of momentum. Conservation of energy is way easier to do because you don't have to worry about directions. Okay, but remember, you do have to worry about that in conservation of momentum. All right, so here's my incident X-ray. So this is before, and then after it hits an electron at rest, the recoil electron goes in one direction, and the scattered X-ray, with, remember, it has a smaller frequency, goes the other way, and this is of course after. So if you think about having to use conservation of momentum, then you're going to need to think about direction. You're going to have to split that up into its X and Y directions and everything like that. And sometimes you have to use momentum. However, if we have enough information to be able to just use energy, because we know this is an elastic collision, and we know that kinetic energy before will equal to the energy after, well, that's going to be so much easier because then we don't have to worry about directions. We don't have to worry about angles. We can just get the energy of the photon before, and then the energy of the electron plus the energy of the scattered photon afterwards, and you're good, right? So there is a change in wavelength. This is the smaller f, which also means, what does that mean? It means a longer wavelength. Okay, so this photon right here will have a longer wavelength than the incident photon. So how do we calculate the change in wavelength? Well, there is this equation on your data sheet for just specifically change in wavelength, which, remember, you can also break it down to this. So instead of just having change of wavelength is equal to h divided by mc times 1 minus cosine theta, you can also just have lambda f minus lambda I, because sometimes you might have one or the other. Okay, really, really important, because so many people forget what the things in this equation represent. H is, of course, Planck's constant. Mass is the mass of the electron. People put crazy things in for that mass. Photons don't have mass. You can't put mass of anything else in there other than the mass of the electron. It's the only thing in this entire situation that actually has mass. So what else would you put in there for mass? C is, of course, the speed of light. And then this angle right here, you're like, which is that? That's the angle through which the X-ray scatters. So, of course, that's this angle right here. It's not the angle at which the electron scatters. It has to be the angle through which the X-ray scatters. So those are probably the two most important that people tend to forget what those represent in this equation. All right, so let's do an example with this conservation of energy and the difference between the wavelengths before and after. So we have a 43.7 kilo electron volt X-ray scattered in a Compton experiment. So the scattered photon has a wavelength of 2.9 times 10 to the negative 11 meters. So that's the scattered photon. So of course that is the wavelength of the photon afterwards, so we still don't have the initial wavelength. We need to determine the angle of the scattered photon. So that's part of this equation right here. We need this angle. So we know, of course, the change in wavelength is equal to h. We have that, m, we have that, c, we have that. So we just need to find the change in wavelength, which we almost have, but not quite. We have the final wavelength, but we don't have the initial. However, we do have the energy of the initial photon. So if we have the energy of the initial photon, can we find the wavelength of the initial photon? Absolutely, because energy of a photon is equal to hc over lambda. So if I want the wavelength of the initial photon, I have the energy of the initial photon. I can just rearrange this equation right here. So my initial wavelength will be hc over E. Okay, we want the wavelength in meters, but if I use the electron volts version of Planck's constant here, the electron volts will cancel out and I'll be left with meters, so that is okay here. So I'm just going to use the 4.14. And just remember we had 43.7 kilo electron volts, so we need to multiply that by 1,000 to get electron volts, and we get an initial wavelength of 2.84 times 10 to the negative 11 meters. Okay, so there's our initial wavelength. So I can calculate this change in wavelength because that's the final minus initial. So let's do that. Okay, so there we go, get our change in wavelength, and we can go over and use this equation, this new equation that I just showed you that, remember, is on your data sheet. So take a look for that. And we are looking for this angle. This is not an easy equation to rearrange, so please, please pay attention. I'm actually going to do it in a few steps here, if you can believe it. So first, I'm just going to get rid of this h over mc in front of the 1 minus cosine theta. So I'm going to multiply both sides by mc, divide both sides by h, and I should get change wavelength times mass times c divided by h is equal to 1 minus the cosine of theta. Okay, so then I would really add cosine theta one side, subtract lambda mc over h to both sides, and I would get something like cosine theta is equal to 1 minus delta lambda mc over h. And then, of course, I'm going to just go right to getting the angle here. Okay, but that's one where if you're having a hard time rearranging that, please make sure you work on it, you make notes on it, and you figure out how to do it before you get to a test. Okay? All right, let's figure out this angle. I am using the joules version of H here because I just have meters, kilograms, meters per second. I don't have another electron volts for it to cancel out with, so I absolutely need the joules version of Planck's constant here. Okay, and then we calculate that and we get an angle of 40.4 degrees. Okay, so again, just be careful with rearranging that equation. It's a rough one. It's definitely not easy to rearrange. So just be careful with that, but you can get it. I have no doubt whatsoever. All right, I have one more example, and this is an old diploma question. And so this one, we would have to use conservation of momentum. So we have one example of Compton scattering shown below. Incident photon has a momentum of 1.83 times 10 to the negative 23 newtons times seconds. Okay. Perfect. It collides with a free electron that's initially at rest. The scattered photon has a momentum of 1.72 times 10 to the negative 23 newtons seconds, 85 degrees from the direction of the incident photon. So that's this guy over here. So its new momentum, 1.72 times 10 to the negative 23 newtons times seconds. Okay, so we want to know the magnitude of the momentum of the free electron after it's been hit by the incident photon. So what are we going to have to do here? Well, because they gave us this angle, it's going to be a bit nicer. But remember, when we're working with momentum, we have to look at our x and y values. So I'm going to need to break this up into its x direction and its y direction. Okay, just like with this one, I'm going to have to break it up into its x direction and its y direction. But the nice thing about this one is you might only have to do one or the other. Okay, so I'm gonna be nice about that one. Just FYI, I'm gonna use I for incident photon. S for scattered photon. And E for the scattered electron. Okay, those are just my subscripts, what I'm going to be using here. So let's go with the x direction. Okay, so this is really just a review of momentum. So we're going to go with the x direction. I'm going to say right is positive because guess what? Everything's going to the right. And we need to know our momentum in the x direction. We of course know before should equal all the sums of the momentum in the x direction afterwards. Before we just have the momentum of our initial incident photon in the x direction, and that should equal to the momentum of the scattered photon in the x direction plus the momentum of the electron in the x direction. Okay, so again, we're looking for the momentum of the electron. So let's find that, and we can just find it in the x direction for now. And so that'll be the initial momentum in the initial photon. And we don't have to worry about x directions here because, of course, it's already in the x direction. And then I'm going to subtract the momentum of the scattered photon in the x direction. So if we look at this guy, the angle's there, so the x direction is our adjacent side, so we need to multiply that by cosine of theta, and then we should be able to get the momentum of our electron in the x direction. Okay, so when we do that, we are going to get 1.68 times 10 to the negative 23 newtons seconds. Okay, so that is the momentum of the electron just in the x direction. So if I want the momentum of the electron, not just in the x direction, but like this whole hypotenuse here, if I know that this guy is 1.68 times 10 to the negative 23 newtons times seconds, this is a situation where it's actually really nice. I don't have to go over to the y direction, do conservation of momentum in order to find the hypotenuse here, because I have one side, I have the angle, so I can just use SOHCAHTOA here. I have the adjacent side, I want to find the hypotenuse, so I'm just going to use cosine, and then I'm going to be able to get the momentum of this electron. If they didn't give us that angle, then we'd have to go and do conservation of momentum in the y direction and go from there. Okay, if you are looking to see what that looks like because you need some a refresher on conservation of momentum, make sure you go take a look at the notes for this example online, because I've done it that way as well. Okay, so here we can just look at the fact that cos of this angle is opposite over, is adjacent, which is the momentum of the electron in the x direction divided by the momentum of the electron. And we're looking for the momentum of the electron. So momentum of the electron is momentum of the electron in the x direction divided by cosine of theta. And what do I get when I do that? I get 2.40 times 10 to the negative 23 newtons times seconds. And there we go. There's the answer. Sorry, I know this page is a bit of a mess. Be nicer to do it on a bigger page, but this is what I got. And there we go. So if we look here, look at that. It's D. And that is our answer. So, yeah, you're going to have to go over conservation of momentum. But remember, if you can use conservation of energy instead, like if you're trying to figure out the speed of the electron afterwards, use conservation of energy. It's so much easier if you can. But if it specifically asks for the momentum, obviously you have to use momentum, and you have to go into the directions and everything like that. But just keep in mind, if you're just looking for the speed of something, use energy. You have the energy of the initial incident photon. You can find the energy of the scattered photon and find the kinetic energy of the electron, and just think about that, because we know all of these collisions are elastic. Our kinetic energy is always conserved. Okay, that's that. Good luck. Go do a bunch of questions. Okay, that's where I'm leaving you at for this long weekend. Good luck. I hope it makes sense, and let me know if you have any questions.